So last time, let's recall, last time we talked about Harris-Kleiman correlation inequality, a cute, a very useful inequality, showing that if two monotone properties, they are same downsets or both upsets, then they are positively correlated. If they have the opposites, they are opposite to each other, one downset, one upsets, then they are negatively correlated. We saw some applications to bounding the size of intersecting families. In particular, these intersecting families are set systems where we put no restriction on the cardinality of the sets. So today we're going to study uniform set system or uniform hypergraphs where we're going to assume all sets in our set system have the same size. This is another central fundamental result in extremal set theory, the Erdős-Corrado theorem. So let's start by recalling some definitions. We have we say a system of K sets is basically we say a system of K sets, or sometimes I say K uniform K uniform family is the same thing on ground sets. And is nothing but you just take a collection of subset of first n integers of size k. So this notation is all k subsets. If I haven't mentioned before, if I'm not sure, this is all k subsets, all subsets of size k. It's just like k subset size k. Good. And we say they are intersecting, abusing the notation a little bit, if they are actually pairwise intersecting. So recall when we say intersecting family, we mean pairwise intersecting. I.e., for any f prime in our family, we have their intersection being non-empty. Now we can ask our question. If you have a uniform family, K uniform family, and we say it's intersecting, how large can it be? In a non-uniform setting, we know the answer is 2 to the n minus 1. Recall question, how large a K uniform intersecting family can a K uniform intersecting family be? So recall, in a non-uniform setting, we know this is at most 2 to the n minus 1, and all the maximal size has to be the same as those of maximum size, which is 2 to the n minus 1. That was an exercise. Things are different here. Maximal size and maximum size are different, but that's something later. Let's first look at what's the maximum size. Let's try to think a little bit. If k is too large, so if n is less than 2k, there's nothing to do. Why? The ground set, the pool is so small that it has no room to put two disjoint k sets just by pigeonhole. So all k sets are intersecting. Then every two k sets intersect, we get max size is n choose k, everything. Not so hard. Let's go a little bit beyond this trivial case. What if n equals to 2k? Okay. So this is n equals to 2k. In this case, let's cut things into half sets. So you can partition the ground set into two k sets of two complementary parts, right? If this is A, this is A prime, each of size k. Cut into two parts. So if a family is intersecting, A and A prime cannot appear both simultaneously in this family F. So for every pair, we lose one. But notice that if you have A and A bar, and you have B and B bar, let's do another one. Now you have B and B prime, B bar. Then every set in one pair is intersecting with every set in another pair, in a different pair. This is not hard to see. With that being said, that means for all pairs, we can choose exactly one. And that's the best we can do. So the max is choose one from each complementary pair. And what's the size? We have 1/2. What's the total number of pairs? N choose k. That's the size. And actually, if you work a little bit, this number equals to n minus 1 choose k minus 1. When n equals to k. So the non-trivial case is when n is greater than 2k. That's what we're going to address. In this case, let's first try to think of a large family. Let's guess the lower bound for the maximum size. So a moment of thought, if you want every pair intersect, the easiest way is to fix an element and make sure that this element appears in all k sets. So an easy lower bound, well, I don't know if I should say easy. If you've seen this before, it's easy, but otherwise it might take a moment of thought. An easy lower bound or an easy way to get a large intersecting family of k sets is to choose all containing a common element. And what's the size of these sets? Lo and behold, it's the same. If you fix an element, then you have to choose from the remaining n minus 1 elements, k minus 1 of them. Right? So this size equals 2. So the maximum size is at least n minus 1, choose k minus 1. And the Corrado theorem is saying that this easy construction containing a fixed element, let's say 1, all these k sets containing element 1 is best possible. For any n greater than 2k, and for any f which is a k uniform family intersecting, then the size of f is at most this lower bound that we constructed above on the maximum size. That's the best we can do. Let's prove this. The original argument of Corrado applies induction on n. Not super complicated, but not the easiest one. So here we will see a very smart double counting argument by Katona. Sometimes people call it Katona circle method. So we're going to see proof. This is proved by Katona. A double counting. So what we're going to do double counting now, we're going to count. So his smart idea is that we're going to imagine elements of the ground set and get placed on a circle. That's why it's called circle method. All right, and what we're going to double counting is there are many different ways. So let me first say the idea. There are many different ways to place elements of the ground set on the circle, right? n minus 1 factorial ways. That's all the possible cyclic permutation arrangements. So for each one such way, we're going to see how many, then we're going to consider arcs, which are consecutive, this kind of interval on the, in this cyclic permutation of size k. And we're going to consider how many of these arcs are sets in our family F. That's what we're going to do double counting out. So let's imagine our elements get placed on the circle. Okay, so this is x1, x2, x3. Probably there's only x3, xi, xk minus 1, xk, right? And at the end, you have xn minus 1. We have n elements on the circle. So let Cn be all cyclic permutations of the ground set n. So what do we know? We know the number of cyclic permutations is n minus 1 factorial. Okay, because cyclic permutation, where you start doesn't matter. So you fix an arbitrary element to start, and then you're going to choose the elements that follows this arbitrary starting point. since already fixed 1, so the choice of the first one following the first element is n minus 1 choice, n minus 2 choice, so on and so forth, n minus 1 factorial. We're going to do double counting. On double count the pairs, sigma f, where sigma is one of the cyclic arrangements of the ground sets, and F is a set in our intersecting family F, such that F forms an interval, which I call it arc, in sigma. So like this. Suppose K is 5, this, for example, if F looks like this will count 1 towards all possible pairs like this. So if F looks like this, it's not the arc because there's gap. I really want a complete interval, everything. So we're going to show that this count, let's let P to be the number of such pairs, sigma F, satisfying this above property. Our goal is to show P, on one hand, it equals to the cardinality of our intersecting family F times K factorial times n minus K factorial. On the other hand, is at most n minus 1 factorial times K. So if we prove this is the claim, then we are done, because the claim would then imply that F is at most, let's do it, n minus 1 factorial times K over K factorial n minus K factorial. If you do this calculation, blah, 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 this is n minus 1, choose K minus 1. I will skip the calculation. So our goal now to finish the proof of Erdős-Corrado is to show that the number of pairs, once again, with a cyclic permutation and the arc of it, the interval of it, being a set in our intersecting family F, such pairs satisfy these two bounds. The first bound is easy. Let me copy this. I will need it later. Okay, I will draw a new one. So the first bound is easy. Let's count it from the point of view of F. Okay. From point of view of F in F, the number of choices for F, obviously, is you can choose anything in F. Once you choose this F, this is my F, then I'm going to permute it in any possible way that I want, then permute F. This is not script. This is a set F, right? Then permute F, the number of ways is K factorial. F is of size K, you scramble it as whichever way you want. After you scramble that, then you scramble the remaining elements n minus k factorial ways. Put them these two pieces together, you get the cyclic permutation sigma. And then the number of ways to permute the rest of the elements, which is n minus k factorial. These two give rise to a sigma in Cn. So we have this equality. Choose F, permute these sets, permute the rest. What about the upper bound? Well, the proof already suggests how to finish it, right? For the lower bound, we view things from point of view of the second coordinate. So for the upper bound, let's start with sigma. So if you start with sigma, obviously, there are n minus 1 factorial ways to choose sigma. So what's left to prove is for any cyclic permutation sigma, it can contain at most k sets from our family F. For the upper bound, from the point of view of sigma in Cn, and there are n minus 1 choices, suffices to show, this is the shorthand, STS, suffices to show for any sigma in Cn, the number of arcs in sigma, let's write it as A sigma. Well, first of all, how many such arcs? Well, there are n elements, right? For any sigma, this is one arc of size k. Shift 1, you get another arc of size k. So you can shift n times, n elements. There are n arcs, n intervals in each permutation sigma. Okay, I'll not write it. Hopefully this is obvious. N arcs. So among these n arcs, the number of arcs sigma that lie in F is at most k. And most k arcs are sets in F. How do we prove this? Well, so far, what we haven't used, the most important hypothesis, right? The families intersecting. We've never touched this yet. And that's the thing that drives everything. We're going to use this intersecting property. The idea, before I write down the detail, is if some arc like this one appears as a set in your intersecting family, then all other arcs can only be those touching these blue parts. And how many of them? I mean, the furthest to the right is this one. The furthest to the left is this one. You can somehow pair them up. Like I pair this one with this one. Then only one of them appear. I pair them up and show that among all these possible choices, at most k of them can appear. So let's write down the details. Okay, proof. Okay, I used too many proof. So let's prove this STS. So let's fix sigma. So let's fix a set F in F intercept A sigma, shall we? Let's fix one that appears to be an arc in sigma. Let's say it's this guy. Let me try it. So this is our F. And let's call the elements of these sets in the cyclic clockwise order, x1, x2, dot, 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 xi, dot, 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 xk minus 1, xk. It's of size k, right? Now, the first write in clockwise order, F is x1 to xk. Now, the key observation is that let's first give name. Let's write EI to be the arc. Ending at xi. Okay, so from here, go up. This is my EI. The arc that ends at xi, that's EI. And the arc that starts at xi, I call it SI. So S stands for start, E stands for end. So SI is the arc starting at xi. So now as F is intersecting, it implies that all sets in A sigma intercept F, all arcs in sigma that could possibly be in F has to be those intersecting F, right? Have to intersect F, which implies that they are from they are one of the sets. They have to be so what's the earliest one that intersect F? The one that ends in x1, right? If it ends before x1, it's disjoint from F. So this one ends in x1 is E1 all the way to, so that's E1. To EK. But EK is just F itself, right? EK is F. Now let's go, which EK is also S1, right? So let's write it. This is S1, is also F. So after S1, we go S2, S3, and the last guy is SK. S2, S3, SK. So it has to be one of these sets. How many sets in there? Well, this is our set F. So let's forget about this. Let's look at here. There's K minus 1 here. There are K minus 1 here. We can actually pair them up into disjoint pairs because E1 ending in X1 is disjoint from S2 starting in element 2. E2 ending in X2 is disjoint from S3 starting from X3. You can pair them up. So we have the pairs, disjoint pairs, EI and SI plus 1, where I goes from 1 to K minus 1, disjoint pairs. So that means F can only take one of these from this disjoint pair together with EK. So F can have at most one from this K minus 1 disjoint pairs. And also F equal to EK equal to S1. So you have at most K as desired. Any question? Okay, there is a question. So let's see. Tier 1 is asking, what if for sigma, none of the consecutive K elements is not F of the intersecting family? Oh, it's possible. It's possible that none, it's possible. We are proving the number of arcs in F is at most K. It could be 0. It could, yeah. We are proving upper bound. For example, if you start your intersecting family just to be a single set F, definitely there are some cyclic arrangements where this single set does not appear. It's possible. Okay. So actually, one can show that, let's look at the extremal example, meaning the maximum size set. Actually, something stronger can be proved. For n equals to 2k, we see that there's multiple extremal example, maximum size. Obviously, we can take this trivial one containing a fixed element, is n minus 1 choose k minus 1. Or we can take these complementing pairs, which happens to also be n minus 1 choose k minus 1. But for n strictly greater than 2k, this trivial one containing a fixed element, let's call it star. These kind of stars are the only maximizer. So let me make this remark. Maximizers or extremal family being either n minus k1 half complementing pairs, complementary pairs. Okay, stars are the only extremal ones. I will leave this as an exercise. Not very easy, but not too hard. So prove that when n bigger than 2k, stars are the only k uniform intersecting families of size n minus 1 choose k minus 1. Now I'm going to do now I'm gonna do something which I think is illuminating. We've done it before. I don't remember for Sperner's theorem or one of them. So this thing is we're gonna rewrite Catona's proof in a probabilistic way. I think it's educational, illuminating, because to develop our way of thinking things probabilistically. So this double counting can be phrased equivalently in this probabilistic counting way. So how do we do it? Well, now what we're going to do, so let's recall this proof. We're double counting all possible cyclic permutations and look at the number of arcs from the cyclic permutation that are sets in our intersecting family F. Now what we're going to do is not double counting over all cyclic permutation. Instead, we choose a uniform random cyclic permutation and look at the number of arcs in this random permutation, how many of them fall into our family F. It's equivalent. Now let's phrase it this way. Let's do it as an exercise together. So let's rephrase Catona's proof in a probabilistic way. Proof. We're going to sample a cyclic permutation sigma uniformly random from all cyclic permutations. Okay, now we're going to consider A sigma, which are arcs in sigma. So this is a random permutation. That means the arcs in this random permutation, cyclic permutation, is a random family of sets, K sets. Let's keep this in mind. So this is a random K uniform family. All right. Now, on one hand, we again going to look at the cardinality of A intercept F. Okay. On one hand, for any cyclic permutation in Cn, remember our claim above. For any cyclic permutation, the number of arcs that could possibly lie in intersecting family F is at most K. So you still need to do this a little argument. So we know from the above claim, this is at most K. Very good. On the other hand, this is true for any instance of cyclic permutation. But now let's look at it from this random permutation point of view. So this is a random set intersecting another given family. This is again random. We can compute the expected size of this intersection. The expected size of F intercept A sigma is what? This is just the sum of the arc A in A sigma, the probability that this arc A lies in the family F. Okay, definition of expectation. Now, this equals to, let's first look at the probability. Since our permutation sigma is chosen uniform and random among all possible cyclic permutation, So an arc, I should probably write it down as sigma is uniformly chosen. All k sets in n choose k appears as an arc in sigma with the same probability. Okay, so that means every k set in F appears in A sigma with probability . One second. Yes, okay, that's right. I was thinking whether I should write actually F in F, then probability F is in A sigma. I think that's equivalent. So now the way I want to explain it is sigma is uniformly chosen. So if now you take an element from A sigma, the distribution of this element A is uniformly distributed over these ground sets, n choose k. Right? So for every element A in A sigma, the probability that A lies in here is just purely the relative measure of F, which is the size of F over n choose k. So we have size of F over n choose k. That's true for every A. Now use linearity of expectation, you sum them up. How many arcs? There are n arcs. So n times this. Here we use linearity of expectation. Now we are done. Because we have a random variable whose expectation we can compute. But we also know this random variable never takes value more than k. All right, put these two together. And we are done. You move terms around to the other side, do the computation. That's the proof. So I want to write it in this probabilistic way because it gives us a recipe, a way of upper bounding a family of a collection of sets, a collection of discrete objects, this random way, probabilistic counting. So let's abstract what's behind this proof. And this recipe we will see it again later in spirits in another scenario. In this in some geometric setting where we want to cover a set with a copy of itself, but dilated with smaller diameter. All right, so how do we abstract the recipe here in this proof? Basically, let me first say in words, I will write the recipe down. We have a discrete family, a family of discrete sets we want to bound the cardinality of, which is F here. We don't bound it directly here. What we do is we somehow make use of a random control group, like a control group when they test medicine. We use a control group generated by this random permutation sigma. So the control group is A sigma here. It depends on these, right? And we see how our family interact with the control group. And there's two things we have to do. First, we have to observe, we have to choose this control group in the smart way, as Katona did here, such that no matter what outcome of the control group, this is like a random thing, the intersection of this control group with our family is never too large, as in this inequality. Second thing we have to do is we can also compute the expected size of the intersection set. And how we're going to do that is we're going to make sure our random control group, if you sample an element from our random control group, the distribution of this element, which is A here, the arc, is a uniform distribution over all universe, where this universe here is n choose k. What that being said is, then the intersection size of this is precisely the measure of our family that we want to bound times the size of the control group, A sigma. A sigma is of size n, right? And this is the measure of f. So let me write this recipe down. The recipe for upper bounding some C, some family of discrete objects. It could be graphs, could be posets, could be permutations, could be intersecting, could be family of sets, any discrete objects. What's this recipe? Well, okay, I actually use A. So let me change this. So suppose we want to bound some family A, family of discrete objects. So the target group is A that we want to bound. The idea is to introduce a control group B, introduce a control group B, and usually random, this B is random. Such that we're going to choose B with the what property, such that the property is, first of all, for any elements in our control group B, I should probably write, pair this recipe up with this proof here, okay? So if you pair this up, this A, the target group, is the intersecting family in Erdős-Corrado, and this control group is A sigma in the proof. Yeah. So if you choose an element in our control group, you choose a random arc in a cyclic permutation. This in random arc is a uniform distribution over all possible k-sets. So for any B in B, this is any B in B distribute, because B is random, so these elements in here is also random, distributes uniformly uniformly over something, over some, okay, let me just say uniformly, I will say vague. Here, in this case, A in A sigma distribute uniformly over n choose k in our proof, right? So if you have this property, what does it imply? This then means the probability that B lies in our target group, the probability is precisely the measure of our family A. And here, by measure, I just means in our setting is the normalized counting measure. So mu f is just the size uniform counting measure over n choose k, right? In the discrete setting. But it could be weighted setting. Maybe the measure mu is not uniform over all k sets. That's possible. What that implies then is that we can then compute how our target group intersect with the random control group. That's then the sum over B in B probability that B lies in A, which then equals to the measure of A times the size of the control group B. Okay? This is probably not so hard. The harder bit is we have to make sure also this random group, when it's chosen, that it does not intersect A too much. That's the second important property. For any outcome of the random B, we must have A intercept B is small. Okay, here small means K in our setting. Then what do we have? We have, this is true for any outcome, and we have expectation. So definitely expectation is less than this small bound here. Okay, then what we can do if this is S, it implies mu of A is at most S over B, right? That's a recipe. We're going to revisit this recipe again later. Let's phrase Erdős-Corrado in the graph theory way. So this is about intersecting family. We can actually state it purely as a graph theory statement. Phrasing Erdős-Corrado in terms of Kneser graph, a very important family of graphs. So first, let me tell you what is Kneser graphs. The Kneser graph, denoted by kg and k, we have two parameters, n and k. This graph, let's say you have vertex at V and E, where the vertex set of the Kneser graph is the family that we've been working with just now. All k sets of the ground set n, and two vertices now are two k sets in n. They are adjacent in Kneser graph if and only if they are disjoint. So S T in V adjacent if and only if they disjoint. So in other words, Kneser graph Kg and K is the disjointness graph of k-sets in N, right? What that means is that every k-set in N is a vertex, and two vertices adjacent if they are disjoint. Good. What's now the correspondence? Well, in this definition, if two sets are intersecting, then in Knaser graph, there's no edge. They form an independent set of size 2. So if a family F is pairwise intersecting, is an intersecting family, then the elements of this intersecting family, which are a set of vertices in here, form an independent sets. So in this way, the connection is intersecting family F in N choose K corresponds is in 1-to-1 correspondence to independent sets in Knaser graph and K. Erdős-Corrado gives the upper bound on the largest possible intersecting family, which then translates to a statement about an upper bound on independence number of Knaser graph. So that's how we phrase Erdős-Corrado in graph theory terms. So then Erdős-Corrado rephrase it, says that for any m bigger than 2k, the independence number of Knaser graph with parameter nk is at most m minus 1 choose k minus 1. All right. Any question about this rewording? Here, let's write some basic statistic. The number of vertices in Knaser graph, obviously, n choose k. And this graph is the regular graph. Every vertex is the same degree where b equals 2. So a vertex is adjacent to all those disjoint format. So a vertex corresponds to a k-set. You have to choose all those k-sets that's disjoint from this round from the remaining ground sets. Those are its neighbor. So you have m minus k choose k ways. That's its degree. Phrasing in this way actually suggests a different way. There are actually many, many ways to prove Erdős-Corrado. So for example, you can prove it from a graph theory point of view by proving this graph has independence number at most these. The spectrum, for example, you can do it from the spectrum information of Knaser graph, which is known, and use some spectrum bounds that relates independence number to eigenvalues of adjacency matrix. But that's a later story. When we get to the spectrum graph theory part. Next, we want to 25 minutes, so that's enough. We want to revisit, we want to connect this intersecting family business for uniform family with one of the inequality we learned before, this Bolobash set pair inequality, which these two things are unrelated, but we can prove something that's interesting. So let's begin by, this is the problem of counting problem. So we're going to do counting maximal intersecting families. Good. First of all, before we count, so what's maximal intersecting? Maximal just means, this definition is probably clear, but let me write it again. This is the family is maximal intersecting if, well, if it is pairwise intersecting and adding any sets to it, it's not intersecting anymore. How do I write it? The simplest way, for any f prime containing f not intersecting, any proper superfamily is not intersecting anymore. Now, if we forget about these, so if you draw, this is the family of all intersecting families. And the maximal intersecting families is just a part of it, some subset of it. Those are maximal in terms of inclusion. Let's first look at how large is these, all intersecting families. If a family is intersecting, then any of its subfamilies is also intersecting. That's trivial. As subfamilies, so an intersecting family are also intersecting. Then we get what? The number of k-uniform intersecting families is at least 2 to the n-1 from k-1, trivially. You simply take a star containing one, element 1, and you take all subfamily of it. And the star is of this size, the number of its subfamily is 2 to that. All subfamilies of a star, for example. Okay. This trivial lower bound turns out to be optimal up to asymptotically in the power. This is a fairly recent result, 10 years ago. So this is a theorem by Pollock, Chagnick-Das, Michel Delcourt, myself, Marian Sharifzadeh. We proved that for any n bigger than 2k plus 1, then the number of intersecting families is equal to 2 to the 1 plus little 1, n-1 choose k-1. So this lower bound is not very far from truth. So if you're careful, you might notice that in Erdős-Corrado, we only require n bigger than at least 2k, we can have this max, this is upper bound. But here we require plus 1. This is actually needed and optimal. So no longer true, remark, n bigger than 2k plus 1 is optimal. I will leave it as exercise to show that prove that there are exponentially, actually at least 3 to the n minus 1 choose k minus 1, many intersecting families when n equal to 2k. 3 to this obviously exponentially larger than 2 to this. Okay, this is exercise. Now, good. So that means more or less we know the size of these sets, the set of all intersecting families of k sets. Now let's look at this subfamily. We want to prove intuitively, we will imagine that this subfamily, since those are the maximal ones, it's much smaller than this. That's what we want to establish. This turns out to be true. So the theorem we want to prove is also in the same paper. The number of maximal intersecting K families, K uniform, on N is at most this quantity. So we're going to prove this bound, but let's keep in mind this bound is at most, if you want to write it in the simpler form, n choose k to the power 2k choose k. And one remark is that this is indeed much smaller. Let's imagine for a moment, if we think of k bounded, think of k is bounded and n grows to infinity. Okay, then the maximum size okay, wait. So we have from the above theorem, we have 2 to the n minus 1 choose k minus 1, right? This is roughly 2 to the n to the k, exponential in a polynomial of n. But what is this? This is total versus maximal. This is roughly, this is the most n to the k, n choose k, times 2k choose k. So this is n to the k times 2k choose k, which is k times 2 to the 2k at most. So you have something exponential in n versus something that's polynomial in n, where if k is a constant, so this is polynomial. This is polynomial. So for this, let's introduce a useful thing of associating a maximal intersecting family to something we call generating sets. So let's start proving this thing. What we will prove is actually, we should actually prove this lemma that, okay, let me state the lemma in a little bit. Let me first write the definition. For a family, given a family, doesn't have to be intersecting family, just a uniform K-uniform family, we write IF to be all those K sets that intersecting all elements in F. So all K sets such that G intersect F is non-empty for any F in F. The family of all K sets that intersect all sets in F. This is the family. All right. If you want to see a picture, if this is F, right, it doesn't have to be intersecting. Then IF will be this, those that have to intersect everything in F. Look something like this. All right. Observation. Let's make some observation based on this definition. If F is an intersecting family, F is intersecting family if and only if F is a subfamily of IF. All right, let me quickly explain. If it's intersecting, then everything in F also intersect everything in itself. So it's this direction is trivial. The other direction is also trivial. Okay, just by definition. Second observation is that equality holds in the first observation when F is maximal. If and only if F equals to IF. So we have a different way of saying when the family is maximal. Equality holds. This is also not hard. So if it's not clear, exercise. Maybe I'll leave this as exercise. Good. Now, given a maximal maybe I'll call this a lemma. Given a maximal intersecting family F in n choose K, there exists a generating set we call it generating set G, which is a subfamily of our family F. Why it's called generating set? Because if you take this I operation on G, defined this way, you take all those K sets, intersecting those, all those in G, you'll recover F. Okay, this is called intersecting set. The name, generating set. The name is that the elements in here, if you take this operation, it generates the maximum family F. So let's first show that this definition of generating sets is well defined. There indeed, you can find something that's in here. All right. I forgot a basic observation here. There's another observation I want to write, is that this operation, if you take a smaller family, this IF will becomes bigger. Because if you have smaller family, you have less constraints here. You have more sets satisfying it. This is the observation. For any F prime, let's say F minus to indicate that this is a smaller family. That's a proper family of F. Then what it generates will be at least as large as F. Maybe equal, but definitely not smaller. So you have the other way containment. Good. So let's prove this lemma. This is simple lemma. Once again, what's IG? IF is you collect all the K sets intersecting everything in this family. In other words, we introduce this transversal, right? Transversal means a set of vertices intersecting everything in here, every set in there. So we're looking at transversal of size K. This is all transversal of size K for F. The proof is basically we can find this generating set by deleting elements from F one by one. Initially, F, by this exercise, it's maximal intersecting, so F equals to IF. Okay, now we're going to delete sets one by one from F. Yeah. So let's call this F0 is F, and F1 means with one set removed. So we have what? If you look at by the observation above, this is F0, which is F. If you delete things, you get smaller family. You look at their I. This is, you go this way, right? Smaller family generates more things. So simply, you just go down this, you take all this thing can be a generating sets, right? Maybe at some point, some Fi, this becomes strict. You get much big strict family. Then you just don't take this Fi. You just take all the previous one, it works. All right. This is a trivial one, but I want to say that this is a way to find the generating sets. Actually, we will prove is that so we're gonna show that for every maximal intersecting family, we're gonna map it to one of its generating sets. So what we would do, the idea to prove the counting results, it's from for every maximal intersecting family, we're going to map it to a generating set of small size injectively. Injective is obvious, right? Because by definition, the generating set, if you generate the family I, it equals to F. So if you start with two different F and F prime, their generating set must be different by definition. So this injective is obvious. So we should prove for any maximal intersecting F, there exists a generating set G in F of size at most. Here's the key thing. We can find one of size at most 2k choose k. Then this is enough to prove the theorem. Why? Let's see. Let's look at what this summation is. Since if you look at the family of all maximal intersecting family, for each one such thing on the left, we can map it to some intersecting family, which is a subfamily of it, right? A generating set. So if you generate, use G, you can generate F. We have this injective map. So every intersecting family can map to a unique, not unique, can map to a distinct generating family of size at most 2k choose k. So that means the number of maximal intersecting family, maximal one, is at most the number of generating sets. And we know that we only need to consider generating sets of size 2k up to 2k choose k. You just simply sum over the total number of k sets is n choose k. Among all k sets, you choose the number of ways to choose a generating set of size 2k choose k is at most this summation. Done. The proof. So what amounts to proof, what remains to prove is this claim. I'm running out of time, so we'll probably do it next time. We're going to prove that every maximal intersecting family F, we can do this deletion. You just go down to the minimum one here in this inclusion. You go down to the last position where we still have equality here. It still generates this guy. And we will show that this is 2k choose k. We're going to create the intersecting set pair as involved by set pair inequality AIBI, where AIBI disjoints and AIBJ are intersecting. And since this k uniform family, the number of such pairs is at most 2k choose k. And that somehow bounds this generating family. All right? Any question for today? So summarize today. Proof. Erdős Corrado. Katona's proof. And we are looking at counting, right? It's counting. After that, we gave this recipe and we move on to counting intersecting family. Yes. Counting number of intersecting families. All right, if there's no question, we're gonna skip once again Thursday's class and see you guys next Tuesday. Thanks for listening.